You've probably chatted with an AI like ChatGPT, right? But have you ever stopped to wonder how it actually reads what you type? How does it go from your sentence to, well, understanding? The answer is way more complex, and honestly, way more fascinating than you might think. And it all kicks off with a question that seems almost ridiculously simple. Okay, so take a look at this. How many words are in this sentence? Gone. Count them. Seems pretty obvious, doesn't it? Well, let's see what the answer really is. So did you get 16? If you did, you're right. But here's the twist. If you counted 18, you're also right. It just depends on whether you count that comma and that period. For a modern AI, that punctuation isn't just decoration, it's a critical piece of the puzzle. This is our very first clue that for a computer, the whole idea of a word isn't nearly as straightforward as it is for us. And hey, this isn't some new problem. Let's take a trip back to the 1960s. A program called ELIZA could actually hold a conversation that felt surprisingly human. Its trick? It just used simple pattern matching on words. It would see a phrase like, "I need something," and fire back, "What would it mean to you if you got something?" Super clever, right? But it was just treating words like solid, unbreakable blocks. We've had to come a long, long way since then. And that brings us right to the heart of the issue, the problem with words. The very concept of what a word even is turns out to be incredibly slippery, even in a language like English that feels so cut and dried. Now check this out. It's a perfect example. When we write it, I'm is obviously one word. But grammatically, it's two separate ideas, right? It's the pronoun I and the verb am. So, which is it, one word or two? An AI has to make a choice, and that choice has huge consequences down the line. And things get even messier when we stop reading and start listening. Imagine someone saying this: "I do mainly business data processing." What do we do with that or the little stutter, that main fragment? Are those words? To a speech recognition system, they absolutely are. They're super important signals. It just goes to show how much context can change everything. Okay, so the problem's already tricky in English, but when we start looking at other languages around the world, our whole Western idea of a word being separated by spaces just completely falls apart. Take a look at this sentence in Chinese. See? No spaces, not a single one. Now, this string of characters could be broken up into 3 words, meaning Yao Ming reaches the finals. Or it could be 5 words. Or you could even say each character is its own unit. There's no single right answer, which is a massive headache if your goal is to build an AI that understands everyone. And this isn't just about Chinese, not by a long shot. Writing systems like Devanagari, which you see right here, are used for more than 100 languages, including Hindi. And they have similar challenges. This simple idea of just splitting the text at the spaces is a very English-centric and, frankly, very limited way of looking at language. All right, so problem 1, defining a word is a nightmare. But then there's a second, even bigger problem. There are just too many of them. This is actually a linguistic rule called Heap's law. And what it basically says is, the more you read, the more unique words you'll find. A language's vocabulary isn't some fixed dictionary you can memorize. For all practical purposes, it's infinite. So think about what that means. You can never build a complete dictionary for an AI. It's impossible. It's always going to run into words it's never seen before. New slang, weird technical terms, people's names, or even just typos. This is what's called the unknown word problem. And for ages, it was a massive roadblock for AI. So how on earth do you solve these two giant problems? Words are hard to define, and there are an infinite number of them. Well, the solution is, and I don't use this word lightly, elegant. Instead of treating words as these solid little atoms, you break them down into smaller, reusable pieces. Think of them like language Lego. This whole process is called subword tokenization. So instead of a dictionary of words, the AI has a vocabulary of these smaller pieces, which we call tokens. These tokens can be common words, sure, but they can also be things like prefixes, like re, or suffixes like ing, or just common combos of letters. By snapping these tokens together, the AI can build a representation for any word, even one it's never ever seen before. So how does the AI figure out what these Lego pieces should be? Well, one of the most popular ways is this really clever algorithm called byte pair encoding, or BPE. It's actually pretty simple. It starts with a vocabulary of just single letters. Then it scans a giant pile of text and finds the most common pair of letters next to each other. Let's say T and H, and it merges them into a new token, Sich.
Then it does it again. Maybe it merges th and e to make the. And it just keeps doing this thousands and thousands of times, building up a vocabulary of the most useful subword chunks it can find.
Now, I know this all sounds pretty technical, but this decision, how we chop up language into these tiny pieces, has enormous real-world consequences that actually affect how AI works for billions of people every single day. Let's see this in action. Here's a sentence that's been run through a modern tokenizer. You can see how a common word like she's gets its own token. But a name like Jane's gets split into Jane and S. Numbers get chopped up into pieces. And get this, even the same word, anyhow, is tokenized differently depending on whether it's capitalized or not. Wild, right? For English, this system is incredibly efficient. I mean, look at this recipe instruction. It's 14 words and it turns into just 18 tokens. Most common English words get their own personal token. It's great, it's neat, it's compact. But what happens when we use the exact same tokenizer, one that was trained mostly on English text, and we throw another language at it? Let's take a look at the very same recipe, but this time in Spanish. And here it is. This is the bombshell. The Spanish version, which has 16 words, explodes into 33 tokens. That is almost double. Look at how common words like hondo, which means deep, and jugo, meaning juice, are just shredded into these tiny, meaningless bits and pieces. This happens because all the valuable vocabulary slots in the tokenizer were used up on English token. So here's the bottom line. For many, many languages, it can take up to twice as many tokens to say the exact same thing as you can in English. This isn't just some weird little quirk, it's a fundamental inefficiency. It's like a hidden tax that's placed on non-English speakers every time they use one of these AI systems. So why should you care about any of this? Because tokens are quite literally the bedrock of modern AI. They are the fundamental atoms of language that these models see, and every choice made at this level affects everything that comes after it. And the impact is huge. More tokens means more number crunching, which makes using the AI more expensive and slower. When a word gets chopped up into tiny, random-looking bits, it's a lot harder for the model to figure out what it means, which hurts its performance. And maybe most importantly, it builds in this deep, systemic bias that favors English over hundreds of other languages. And hey, don't just take my word for it. As the source material for this explainer puts it directly, this fragmentation isn't some small technical detail. It creates this cascade of problems. The AI understands things more poorly, costs go up, and you need even bigger models just to overcome this basic handicap. So the next time you're chatting with an AI, just remember what it's really seeing. It's not our words. It's a stream of these tokens, these statistical language Legos, which kind of leaves us with one last big question. If an AI's fundamental building blocks of language are so completely alien to our own, what does it really mean for it to understand us at all?